Word. Okay, so let's get started. So before we begin the lecture, are there any questions about course logistics or any course material? Okay, so everyone submitted your project proposals, so that's great. So it looks like we have some really interesting projects. And I've given all the groups feedback. So if you have any questions about the feedback, feel free to follow up and ask for clarification if you need it. The main thing to keep in mind, and the feedback I've given to some groups, is make sure the presentation is about MRI. So for example, it's okay to apply an algorithm, bioinformatics algorithm or some algorithm to the MRI, but it should not be a bioinformatics presentation or a cancer presentation, or so it's okay to provide some background, but just make sure that you are relating it to course materials, and that whatever simulations you're doing, that they're a little bit beyond sort of what a basic simulation would be in terms of, it's just like plotting a curve. That's probably okay, but that's not going to get you many points on the difficulty component. And so in terms of looking at how Professor McVeigh and I looked at the CT project one, I think, where groups maybe were a little bit surprised by sort of the scoring was because sometimes the presentations sort of veered away from the subject material. Okay. Or else the computational part was essentially just plotting some curve or something like that. So, you have a sense of sort of the level of difficulty of different groups from project one. So just keep that in mind as you're doing project two. We want all of you to do good projects. And so if you have any questions or need help, just please feel free to ask me. We want you all to succeed and have great projects. Okay. So are there any additional questions about projects then? No? Okay. So today we're going to finish up our discussion of arc excitation. And then we're going to take a little bit of a detour into sort of the linear algebra perspective of MRI. And this has not been something that we've done too much in the past, although last year we did it, and I've done it one previous year, but it's becoming more and more important, especially with deep learning and new ways of doing MRI. So, and in fact, I think 3 or 4 of the projects are on compressed sensing or deep learning. And so this way of looking at how to reconstruct images is become more important for anyone who's doing medical imaging or any type of medical imaging. Okay, so we're going to talk about that some today to give you some basics, and it'll be a small exercise on the homework 6 just to get you familiar with that. It's basically just running the code and commenting on it, so it's not too difficult. And then we'll pick up again next week so that you leave this course at least with an understanding of where's the field going, and so that, because basically what we've learned so far is 20 or 30 years old. Okay, basically the stuff you learned before you transform, and that understanding has been known for a long time. So what we want to do is, even though this is an introductory course, we want to at least give you the tools to sort of understand where the field is going. Then we'll go back to some more traditional material, talk about relaxation, creating spin echoes, and start talking about how do we actually start getting image contrast? How do we get information out of the MRI signal? After we made the image, that's just the first step. Now we want to sort of say, well, what's interesting in our signal? What can we tell about the biological system by looking at our signal? And how do we accentuate different parts of the biology? All right. Oh, so before we start, let me just say a few words about the pre-lecture quizzes. Just to remind you, in resolution, and for this one, I realize that there might be some misunderstanding of what higher or increased resolution means. And so increased resolution just means as I'm going from here to here, that's increasing the resolution. Okay. But this also means the delta is going down. Okay. So that might be where some people got confused. So I'm going to actually go through and for those people who picked the opposite and have that interpretation, I'll just add a point for that. So if you thought that increased resolution meant increasing the delta, for next year, I'm obviously going to clarify that. But for this year, since I realized as I was seeing the inputs coming, I was like, oh, why are people picking this one? I realized it's probably because they're thinking that I meant increased resolution meant increasing delta. But actually increasing resolution in imaging is always decreasing the voxel size. Okay, so that's good to keep in mind. But I will, because it's a little ambiguous, I will just go ahead and manually give a point to people who pick the opposite. The other place where I sort of noticed that there were some issues is looking at that spin warp readout gradient. And one thing that the job of that readout gradient, the initial readout gradient, is to get you out to some point minus kx max minus ky max. Okay, so get you out to some point in k space, so that then you can sort of go take a line across k space. Okay, or this full distance here is my wkx. So I think for one of the problems, people were off by a factor of 2 because they took into account this whole width. Okay, but really the problem just asks you to go up halfway, and so therefore you only need half the time. And so if that was an issue, then that's just what happened there. I think the other issue came up with is in terms of, once again, remember the delta kx and readout and the spin echo is always just the area accumulated in each one of those little delta t's. Okay, so delta t is held constant, and let's say we, I forget whether we increase or decrease the FOV, but let's say you increase the FOV, right? If you increase FOV, that means delta k has to get smaller. Conversely, if you decrease the FOV, that means delta k has to get bigger. Okay, so that means your delta k is either gotten bigger or smaller. But if you have the same number of samples, then the width you span is just n times delta k. So that's going to change, right? So it's either going to get, that width is either going to get smaller or bigger, and therefore the maximum frequency you're going to get is either going to be larger or smaller. So that was sort of what that problem was trying to get at. Okay, so if there's any follow-up questions, feel free to send me the question. I think I do see the comments on the, if you comment on the problem itself, I do get those in the daily thing, but it might be a little bit, if you have questions about quizzes, just also post it to Piazza, because that occurs more sort of in real time, and I can answer those. All right. So any questions on that? Okay, so let's move on to the subject matter. So just to remind you where we left off last week, we are talking about RF excitation. And remember, the RF excitation, the job is to take our magnetization and tip it away from equilibrium, such that now we have these spins that process around, and we can manipulate their phase now to create images. Okay. And if you have a uniform field, then all the spins will tip over the same amount, and that's called non-selective excitation. So that's shown here. So this is non-selective excitation. And this might happen, for example, this is done, for example, when we do what's called 3D imaging, where we excite like the whole brain. And then we do a 3D Fourier transform, which we don't do in this class because it's just a little bit too much. Okay, but in practice, we do actually do 3D Fourier transforms. But when MRI was first developed, it was much more, and still today, this day, it's still very common to do what's called 2D imaging, in which case you just want to excite a slice, okay? And therefore, we want to find a way that we can just excite a slice of excitation within some bandwidth, some delta z. Right? So that's shown here, where we have m to z. The magnetization's all, the longitudinal magnetization is 1 everywhere. Then after the selective excitation, it goes down to 0 here. And in the transverse plane, initially there's no magnetization in the transverse plane. After the excitation, then we have full magnetization along the transverse plane. So we've taken, in some bandwidth, we've taken all this longitudinal, and with a 90-degree flip angle, we've converted to transverse, but it's only within some delta z. This is another picture that sort of gives you a sense of how we do that. If we apply gradient And the S test here stands for slice select. So there's very common nomenclature in MR. So typically the Z direction is the slice select direction. And so if we apply slice select gradient here, then this is going to make spins process at different frequencies. Okay, so this is shown by these different sinusoids. So that means to excite these spins, if we can just apply frequencies in this bandwidth, then we're only going to give these spins the resonant frequency they need. And these spins here, because they want to process at a different frequency, if our pulse only has these frequencies, then they're not going to be excited. Okay, so remember, to excite the spin away from equilibrium, you have to excite it with its resonant frequency. Right? If you excite it with some other frequency, it's much more likely to just stay close to the equilibrium point. So this was the picture we had last week, which we talked about. So here's the thing: we want to excite some spins in some interval of delta z. Okay. We apply a gradient. Okay. And so then we can talk about what bandwidth of spins do we have? What's the, basically the spin at in the center, we're going to call isocenter. So that's our reference spin. So we'll assume that this has some delta frequency of 0, right? It's our reference point, so we're assuming that this spin here is going to have some delta f greater than 0, and it's going to have some delta f less than 0. Right? So we're going to have a bandwidth of spins, and if we look at that, we can say, well, we have a bandwidth of spins, and so this rect of f over bw, where the bandwidth is just gamma over 2 pi times gz times delta z. So we know that we have an expression for given a gradient, and the size of our slice, we know what the frequency of spins we want excited. So then our job as the MRI engineer or physicist is to come and excite it with a waveform like this, where this is now a function of time. This was a function of frequency. So we had rect of f over bw. If I take the inverse Fourier transform of this, rect goes to sync. And so using the scaling theorem, this bw on the bottom comes on top. We ignore the scaling factor in front. We just look at this bw times t. Okay. Remember, sync of bwt just means that the first 0 occurs at 1. So that means the first 0 occurs at 1 over the bandwidth. Okay. So let's call the first 0 big T. All right. So that's pretty cool. That means if I apply a sync pulse in the presence of a gradient, I will only excite the spins in a certain band. And this is the basis of slice selection. And so if you look under the hood of any MRI pulse sequence, you'll see the term sync a lot. There's sync pulses everywhere. Okay, so let's go through this problem together, and then we're going to have some exercises for you to do in class. So this is a very common problem where you're saying, well, I want to excite something 10 millimeters. So we know that delta z equals 10 millimeters. Okay. And I'm told that my sync pulse has some bandwidth, has the first 0 at t. Okay, where this t equals 400 microseconds. But we just said, well, hey, bandwidth is just equal to 1 over t. Okay, so that's pretty easy. And we said also, bandwidth is equal to gamma over 2 pi gz delta z. So we know this. We want to design for this. We know this. So we can just solve for g sub z. Okay. So we'll go through that in a minute. And then the next question it says is, well, you're told that this is a sync pulse with an amplitude of A. So then the question is, what is A to get a 90-degree flip angle? And so we'll look at that in the next slide or so. But the bottom line is, this is fairly straightforward, right? That's a design equation you can write down in just one line and then just solve for g sub z. Okay, so in fact, if we do that, we get g sub z equals 0.587 Gauss per centimeter. Right. So now we've designed the gradient amplitude. So that's great. The next thing that computation that's typically done is what's the amplitude, right? Remember, the bigger pulse I put in, the bigger the flip angle. So now I want to figure out what amplitude of pulse do I need to get a 90-degree pulse. And so here, once again, we remember that the theta is just equal to gamma times the area under my pulse. And that just means my pulse is A times sync T, so it's just the area, gamma times A times the area of the sync. But remember, we don't want to have to integrate the sync pulse, right? So we can go back to the Fourier transform and say, well, the area of a function is just the Fourier, its value is this Fourier transform evaluated at f equals 0. So we can do that. And it turns out that that is just T, okay? Because sync of T over T goes to T times rect of ft, and therefore at 0, this thing is equal to 1, right? The rect function is equal to 1, right, at the origin. So I just end up with gamma times AT equals pi over 2. And so therefore I can solve and say, well, then A is just equal to gamma over 2, 1 over gamma T equals 0.1468 Gauss. Right. So what does this tell us? That tells us if I want to excite a slice, and I have this pulse, sync pulse, I need to use a B1 radio frequency pulse that has an amplitude of about 0.15 Gauss. It's a fairly small magnetic field, right? It's about a third of Earth's magnetic field. So that's another thing to remind you that we're always dealing with these really big differences in the magnetic field strength, where our main field typically is very, very strong, unless you're doing cortical MRI, in which case one of the presentations will be on cortical MRI, in which case you'll use a much less field strength. But for the clinical scanners that are in practice now, there's a one very strong field, and all the other fields we use are on the order of the Earth's magnetic field. Okay, so let's this is a good problem to just sort of think through. So, and we'll just open up the poll for this, and then we'll do it in person as well. So you design an RF sync pulse to excite a slice. So delta Z equals 2 millimeters, equals 0.2 centimeters, right? And I said that G sub Z equals 2 Gauss per centimeter. Now, as very common, the user just goes and says, I don't want a 2 millimeter slice, I want a 4 millimeter slice. So delta Z changes to 0.4 centimeters. Okay. So the question is, what should we change G sub Z to be? All right. So go ahead and think about that. Feel free to discuss that with your partner or your neighbors. And I'm going to post this on to launching the poll on Zoom. So if you're on Zoom, you can answer there. We'll do a voice poll here. So go ahead and take a minute or two to think about that and see what you think. Okay. About another minute. Okay, so let's go ahead and if you're in person, at the count of 3, just yell out what you think is the right answer. 1, 2, 3. Great. So A seems like it's the right answer, and in fact, most people voted for A on mine too. So yeah, pretty straightforward, right? We know that bandwidth is the same, right? Because we haven't changed the sync pulse. So it's gamma over 2 pi gz delta z. So this went down by this went up by a factor of 2, right? So therefore, this must go down by a factor of 2 to keep the bandwidth the same. All right? So that's fairly straightforward. Okay, great. So everyone did well in that. So here's your next problem. You design R sync pulse with the first 0, so T is set up such that you excite a delta Z of 0.2 centimeters with G sub Z equals 2 Gauss per centimeter. And now the delta Z is also once again increasing to 0.4 centimeters, right? Now GZ is constant. Okay, so you're not allowed to change the gradient now. So obviously you can only change the RF pulse. So the RF pulse has both an amplitude and this first 0, which is equal to the bandwidth, right? 1 over the bandwidth. So now the question is, okay, for whatever reason you're now, maybe you're maxed out on the gradient, you can't increase the gradient or change it at all or whatever. So now the question is, what do you have to change about the RF pulse? And it's both involve amplitude and where that first 0 is, or the bandwidth of the pulse. Okay. So go ahead and look at that problem, and once again, feel free to discuss. Okay, about another minute, please. Okay, great. So there's been good response online. So let's go ahead and see what the in-person crowd thinks. And once again, just take your best guess. So at the count of three, just sort of say very loudly what you think the best guess is. Okay, 1, 2, 3. B. B. Great. Okay. So consensus B, that was the slight leader. B got 43% online, and it seemed like it was consensus here in person as well. So that is the correct answer. But let's work through it together just so we're all on the same page. So we know that bandwidth is gamma over 2 pi gz delta z, right? Gz is held constant, right? And then delta z we increased by a factor of 2, right? So that means the bandwidth went up by a factor of 2, right? And that bandwidth we know is 1 over t. So that means that t must go down by a factor of 2. So we know that it must be either B or E, right? And the only difference between those is that the t must go from t to t over 2. Right? And the only difference between those is whether you increase the amplitude or decrease the amplitude, right? But we know we want to keep the area the same to get the same flip angle. So we've squeezed the pulse, so it's got less. If we didn't do anything else, the area would decrease, right? So therefore, we need to double the amplitude such that the area stays the same. Okay. So the correct answer then would be B. All right, any questions on that? Okay, great. So what we've just gone through is what's called a slice lecture gradient. And this is now we're starting to fill in what an MRI pulse sequence looks like. So previously we've talked about these gradients. These do, for example, a spin warp pulse sequence. On your homework, you'll find other types of gradient patterns. So spin warp is just one kind of gradient pulse sequence, but it's very common. But there are many other kinds, some of which you'll explore in your homework. This slice-like gradient is what we talked about. Okay. But it turns out and this is the RF pulse, the sync pulse. And so we play the RF sync pulse out in the presence of the slice-like gradient. It turns out though, if you just stopped here, you wouldn't really, you're not done yet. Okay. And it turns out that here you have selected the slice, but all the spins are out of phase. Okay. So you've tipped them all, but they're at different orientations. Okay. So what this gradient is doing is called the slice refocusing gradient. That gradient then gets them all back in phase. Right. So previous years we've gone into more depth in this. For this year, I just want to sort of give you sort of the minimal you need to know about slice selection. And so just for now, just realize that this is a slice refocusing gradient, which is needed to get the spin into phase. So what we're going to introduce now is the term gradient echo. Okay, so we're going to introduce two terms today, gradient echo and spin echo. Okay, gradient echo just means the experiment is this: I tip the spins in the presence of a slice-like gradient, I refocus it, and then I just acquire my data. And here, at the halfway point of this readout gradient, I'm at kx equals 0. Okay. So for example, if I was at kx equals 0 and also ky equals 0, that means all the spins should be in phase at that point. And that's when spins are in phase, those are called echoes. Okay, when we can get spins back into phase. And so this is called a gradient echo because it's the echo that forms after I play out these gradients. Right. You can also just think it's when we're at the center of kx equals 0, the center of k space in the X search. Now I'm just going to talk through the next few slides just to give you a sense of what you can do with these pulses. So right now we've only talked about a very simple pulse exciting a rect function, right? And we said, well, to do that I needed a sync function. And those are just Fourier transform pairs. So the question is, well, what if I want to excite some other pattern? Like, what if I want to excite a cosine or something? It turns out that the answer is actually pretty amazing. You just use the Fourier transform as your RF pulse. So for example, to excite a cosine wave pattern, I could just use 2 pulses because I need 2 direct delta functions. And so this is this thing called multidimensional excitation K-space, where you can think about, we've talked about K-space in terms of imaging, but we can also use K-space to form these RF pulses. So this was first actually invented by John Pauly when he was a grad student at Stanford in the late 80s. So this idea of how do you make these pulses, and now is a standard way of doing pulses. So the idea is that essentially this is the Fourier transform of the pulse, the waveform I want. And so as I'm laying down this energy, I'm also using this gradient. This gradient is allowing me to go through K-space. So one way to think about it is, you're essentially, every time you have an RF, a little bit of RF energy, you're laying down some spins, okay? And it's almost like 3D printing. It's like I lay down some spins and they're at some pattern in K-space. I lay down some other spins, they have another pattern, spatial pattern. And by layering all these spatial patterns on top of each other, at the end, I get the spatial pattern I want. All right. So it turns out that this is a really useful and fascinating area. For example, if I want to excite a circle, okay, then I can just take the Fourier transform of a circle and use that to, and the R pulse would sort of look like this, and the gradients look like this. So basically, this formulation tells you exactly how to play out the R and the gradients. You can get even more acute. So this is sort of an interesting example where I believe this is the author's wife. So he took a picture of his wife, okay, took the Fourier transform of that, okay, and used that Fourier transform to program the MRI system, both the RF and the gradients, such that he excited a phantom. He thought I had a phantom of water or agar or something, some inert object, and he manipulated the spins in that object using this RF pulse. And then when he took an image of that object, it basically, the spins had arranged in a pattern that looked like his wife, which is either cute or creepy depending on how you look at it. But it sort of just shows you the power of this formulation, that you can take any arbitrary pattern and actually imprint that pattern into the spins. So this is a cute demonstration, but where it's useful is, for example, a very simple example is cardiac tagging, where you might want to look at, in this case, you're laying down lines. Okay, and these are not lines you're drawing with a pen. These are actually lines. You're generating a cosine pattern actually in the object itself. So the spins are varying in a cosine pattern. And since those are actually in the object, when in this case the heart beats, those lines will follow the object and deform with the object, because you basically imprinted those lines in the spins. Okay, so when those spins move and you take an image at a later point in time, you'll actually see that deformation. Okay. So obviously, if you're a bioengineer, then you're like, well, gee, if we're a mechanical engineer, like, oh, cool. Now I can look at things like stress and strain. Okay, and so this is a method that, for example, is done, in the cardiac mechanics group here in the bioengineering department, where they'll use methods like this to look at cardiac stress and strain. Okay, so that's all we're going to talk about RF excitation for this quarter. So before we move on, any questions about that? Okay, I don't see anything online. So we're going to switch gears a little bit, and we're going to revisit imaging. Okay. And so far, we've talked a little bit about how, I have an object in what I call image space. What I'd ideally like to do, MRI gathers data in K-space or the Fourier domain. Okay. And when I have this data, I can go back and do an inverse 2D Fourier transform and go back to here. Okay. So let's look at this process of the 2D Fourier transform. So this is just the expression for the 2D Fourier transform. And you can sort of see it's just a double integral over dx and dy. Okay. And the way this is typically done is, obviously in MATLAB, you can use FFT2. But if you had to write the code yourself, this is actually done as sort of two Fourier transforms applied in series. Okay. For example, I can do this integration over dx first, so I can integrate out the x term. And so I'm just left with, instead of gxy, I'm left with a hybrid function gkx comma y. And now I have this, and I can just integrate that over y, and then I get my full term. So one way we've thought about this is one way you can compute Fourier transform is a series of 2D, 1D Fourier transforms. So that's a very useful way, and obviously in your homeworks you use FFT2, and you don't really have to even think about it. But that's sort of, if we think about it that way, it's very useful, but it's sort of limited to Fourier transforms. Okay, and so everything we've done up now is Fourier transforms. But where the world is going is really what's called beyond Fourier. Okay, so Fourier imaging has been super useful, but with the advent of computers, now the world is going beyond Fourier. Okay. So in your homework, you'll play around with some code to do this, which you'll just follow along the code. But here's the idea that this is the picture we've looked at so far. And to get any point in K space, right? Remember, I just multiply this object by some phasor pattern and then put the value at that point in K space, right? And then to get another point in K space, I multiply another phasor pattern and put that in K space, right? But now let's think about another way of looking at this. I can take this object, which in this case has, nx columns and y rows. And what if I just sort of like stretch that into a vector, one long vector, right? So now I just have this one long vector, right? And so this is my image stretched out into a vector, right? So I've taken this 2D image and made it a 1D vector, right? And now I can also take my whatever complex phasor pattern I have in 2D, I can also just stretch that out. And the way I could do that is, for example, if you do, for example, an M:colon command in MATLAB, it just takes things column by column, right? It takes this column and it stacks it column by column, all right? I can do the same thing with my phasor, right? And so this multiplies, I'm just taking this guy and multiplying by this guy, right? So it's just an inner product, a very simple inner product, okay? So, and this row here, I just changed for every kx and ky, I just have a different entry in this vector, right? And so each time I do this multiplication, that ends up with some value, gives me my value of the Fourier transform at some kx, ky. So what I've done now is I've taken what is sort of a 2D problem and converted it into a 1D problem. And now I'm in the area of linear algebra, so now I can apply all the tricks from linear algebra to understand what's going on with imaging. And then when I do things like compressed sensing or deep learning, I'm in this framework where I'm just estimating vectors. And there's lots of smart people in the world who have figured out how to do that in many different ways. And so I can take advantage of all those tricks. You can do the same thing with CT. Okay, and so all of medical imaging is pretty much going this direction where we want to frame our problem as a linear algebra problem. Right? So I have some vector here, which is equal to some what we call the encoding matrix multiplied by another vector. This is what I measure, right? This is what I want to estimate, and so you can sort of see it's a very standard solving a linear algebra problem. So this is what it looks like, and actually in the homework, this is exactly the images you'll see in your homework. For example, I might have this object, and then I have this 2D Fourier transform. I just vectorize both, okay? And then I compute this encoding matrix. And so this is the signal. This is just a 2D sync function stretched out into a vector. And this is just this 1D image, this 2D image also stretched out into a vector. Okay. This is just give you a sense of what the code looks like. So the code is attached in your homework, so you can just look at it. But essentially, you sort of see here we have this. Here's where we're creating our phasor, right? And then for the encoding matrix, you sort of see this is G:, right, which is stretching that 2D encoding matrix into a vector. And we're just putting those columns into our coding matrix. And same thing with our object. Our object, we're just making it into a vector. So this is object vector. Okay. And then once you're there, then you can very quickly calculate the Fourier transform by just taking that matrix times your object vector. Right? So that's all that's done there. And then if you want to, then you can always reshape it back to 2D. Right? So you take things that are 2D, make them 1D, and then at the end, you can reshape them back to 2D. So let's go back down and review a little bit about linear algebra, right? So most of you, the first time you saw linear equations, it was number of equations equals number of unknowns, right? So you should be able to solve it, right? And so that happens obviously when E is a square matrix. Okay, so you could always say that M equals the inverse of E times S, right? That would be your estimate. Right? Given that this is the measurements and this is the image, you can always invert and solve for M. But it turns out E is orthonormal, which is something you're going to explore in your homework, which is basically the columns. Sure, orthonormal means the dot product is just 0 between these columns, right? And that's something you'll explore in your homework. And therefore, the inverse is just the Hermitian transpose, which means you sort of take the transpose and then complex conjugate it. Okay. And so that's also done in your homework for you. So this is basically the inverse Fourier transform. Okay. So remember in the Fourier transform we have e to the minus j 2 pi kxx plus kyy, and in the inverse transform we have e to the plus j 2 pi kxx. That's basically this conjugation step. Okay. So this is what we've done so far, and this is what sort of if you're doing with Fourier transform, this is the only sort of problem you can solve easily. But as most of you know, we have also the other type of thing you probably experienced in linear algebra is overdetermined, right? Where you have more equations than unknowns. Okay. Therefore, what's the problem with when you have too many equations? When you have more equations than unknowns, is there a solution in general? No, there may not be a solution, right? That's consistent, right? Because you can have two equations that contradict each other, right? So in this case, we're not going to be able to come up with an exact solution, but we'll come up with our quote best solution. Okay? And that is all what's called the least squares estimate. Okay? And that has this form, which some of you may recognize. This is a fairly standard form for a least squares estimate with overdetermined equations. And this minimizes S minus my estimate of S. Okay, so that's just saying, I want to just, even though I can't come up with the exact solution, at least give me the solution M that when I multiply by E, minimizes the distance between S and my E to M hat. All right, I'll show a picture of that in a minute. And then also, you probably remember dealing with other determinant equations, right? Where the number of equations now is less than the number of unknowns. So what's the problem with that? How many solutions can you come up with now? Infinite, right? So now the problem is, oh, I have so many solutions, which one do I pick? The answer here is you're going to pick the minimum norm estimate. Of all of the solutions you could come up with, you're going to pick the smallest one. So that's called the minimum norm estimate. Right. And that has this form. It's very similar to this, but sort of different enough that it's confusing. Now the inverse occurs here, and EH occurs here. So sort of these two things are flipped. And this just minimizes the norm or the size of my estimate. Okay, it's like, I don't know which is the best one, but I'm going to pick the smallest one. Okay. So let's see. So this is what it looks like with the square. So in the square case, life is easy, and you can just say M hat is equal to, you could take the inverse if you want to, but that's computationally inefficient. It's much easier to just take the complex transpose. All right. And so that's exactly what's done in the code that you'll see in that homework. Now, how do we get overdetermined equations in MR? Well, that occurs, and this problem didn't really occur until 20 or 25 years ago, where people start saying, hey, what happens if we have multiple channels? Instead of just one coil, what happens if we have multiple coils receiving? So we'll develop this in a later lecture, but today I'm just going to motivate what this means in terms of linear algebra. It means that you get a signal from each coil. Okay, so coil 1 is going to receive a signal, coil 2 is going to receive a signal, coil 3 receive a signal. So for example, this is the head, and these are different coils. You can sort of see each one has a different sensitivity pattern. Okay, so if I put a coil here, it's going to be more sensitive to the brain region close to that coil. And here, it's going to be more sensitive to the brain region close to that coil. Okay, so essentially, every coil now has a slightly different picture of the object. And that diversity actually becomes very important because that's what is going to allow us to go beyond our Nyquist limit. Okay. What that means from a linear algebra point of view is now instead of just one square matrix, okay, I can imagine 3 coils. Each of them is sort of this data is equal to this encoding matrix times my original object. And I'm also going to multiply by this C1, which is a diagonal matrix, which is sort of encodes the sensitivity of that coil. Right? So now I have an overdetermined system. Question? That's okay. That's a great question. So the way you're going to do it is you're going to so the question is, how do you combine all these coils, right? So that's a great question, and we'll talk about that a little bit later. The actual people have come up with many different ways of doing that, and it's fairly standardized now. But the general framework is you're going to write it as this linear equation and just solve it, because this is the best you can do. You're saying this is the data I acquired, this is what I'm trying to estimate, and this is how the data were created. So I'm just going to look for whatever m minimizes the error. And that turned out to be a pretty good solution. Okay, so that's, and you could solve it, but then the problem is these problems get really big. And so it's very hard to solve it just in MATLAB, like, just do inverse. So typically people have come up with other ways of solving it. Okay. So that's an overdetermined system where the way to think about it is what you measure is out here, right? And E m hat is because the number of columns here, right, is less than the number of rows, the space spanned by these columns is like some lower dimensional space where S can be in a higher dimensional space. So the best you can do is figure out what in your low dimensional space is closest to this, what you've measured. Okay. And it turns out the very important concept is the principle of orthogonality, which means this error is minimized when this error is orthogonal to your model space. Okay? And so if you do that, then and you write that now what orthogonality means, then it allows you to very easily write down the equation. So this framework allows you to, otherwise you have to do a lot of algebra and it'll take you forever. But if you just remember this principle, that the error is always minimized when it's orthogonal. Because if I pick any other line, right, and the other solution is going to be longer than this one. Okay. So we'll revisit this when we talk about parallel imaging. And then the last thing we're going to talk about is what is the case where you end up with underdetermined systems. So remember, if I'm fully sample and case space, I have this square matrix, and so I can go from here backwards and forwards pretty easily, right? Undersampled acquisition is here. Let's say I get rid of every other row here in this matrix, right? Okay, that's like skipping every line in KY. And now when I come up with a minimum norm estimate, it just follows this, and then I end up with this earliest image. Okay. So in your homework, you're just asked to verify that occurs and try out different undersampling factors and sort of play around with it and see that. If you just sample that matrix at different rates, you end up with aliasing. Okay. So obviously what we're headed towards is how do we use multiple coils and this framework to get rid of that aliasing? Because what I'd like to do is I'd like to undersample and not have this aliasing. And the way you can see it, let's skip this for now, is this. Here we have undersampled, right? But now let's say I have 3 coils. Now I've gone from an underdetermined set of equations to an overdetermined set of equations, right? Because I've added more data, right? So now I should be able to get a much better estimate of this. Okay. So that's where we're going to, so some of the projects will, you can certainly use these slides, as part of your background in terms of framework to motivate it, but we'll revisit this probably next week in terms of, we'll end the course with sort of sort of give you background in terms of where the field is going. I think the only slide I missed was this one. This is just showing that, in Underdetermined, you might come up with all these equations, all these solutions here would work, okay? But the minimum norm is just picking the smallest one. So that's all it's doing. Right. Okay, any other questions? So that's just sort of to give you some background. So that when you do that, it's a fairly small MATLAB exercise. You just run the program and just comment on it, but at least this gives you some background in terms of why we're doing that. And then we'll probably have another very small exercise on the upcoming homework to give you some more insight into that. Okay, any questions? All right, so now we're going to spend this last half an hour talking about relaxation. Okay. So we already talked about this a little bit. Now we're going to go into some of the details and then talk about how do we make our images to get different contrasts. So remember, there's two main relaxation time constants, T1 and T2, and these are time constants. And this is the return to equilibrium of some Z, and this is the return to equilibrium of MXY. Now you will also see in the field terms like R1 and R2, and these are just 1 over T1 or 1 over T2. So these are relaxation rates. Okay. So when you're looking at something, it's very, very important to see, are you looking at a rate or a time constant? Because otherwise it can be sort of confusing if you don't realize, oh, they're talking about a rate versus a time constant, and just those are 1 over each other. Okay, so this is the picture we had before where magnetization decays very quickly, typically in the transverse plane that's governed by T2, and then it recovers typically more slowly along subsidian, that's T1. We also talked about how different tissues have different gray matter, and there's also this dependence here on magnetic field strength. So you notice that the T1s are getting longer, the stronger my field is. So I want to understand a little bit about what causes this. So it turns out that there is basically the relaxation is always due to dipole-dipole interactions. Okay, and so what happens with MR is every little, like we have the main magnetic field, right? But every little proton is its own little magnet, right? I mean, we said every proton has a magnetic moment to it. So we also have to take into account that not only do we have this main field, right? We have all these other little magnets around us, right? That are going to change what field I experience. Okay? And they're also going to exchange how much energy I experience. So T1 recovery has got to be when things are changing states or giving me energy that can return me back to equilibrium. So basically, remember, I mean, to flip me away, there was energy that flipped me away from equilibrium, right? But if I just added a little more energy, I keep flipping, and if I added more energy, I can flip all the way back. Okay, so things tumbling around me can also send me back to equilibrium. Okay, they can tip me back into the equilibrium state. So what's shown here is, oh, sorry, this is the T1 relaxation rate versus tumbling rate. And so this is either fast or slow. And this is what's called, I think in the website that I got this from, this is what's called the Goldilocks principle, right? When you're just right, when the frequency is just right, and this means low more frequency, then I can tip you back into equilibrium. Okay, and if I'm away from that frequency, I'll try to tip you back to equilibrium, but I really can't do it. And so if the vibration of the surrounding spins, or the lattice, is at the right frequency, then I can return to equilibrium much faster. Right? And if I'm too fast or too slow, I don't return as fast. So there's this typical U-shaped curve here. Right? And so this is this sort of this figure is just showing that, for example, if I have a proton like this, it's going to have some field around it. So as it rotates around, it can create a time varying magnetic field. Right. So here's Goldilocks again, tasting the 3 different bowls of oatmeal, and obviously she wants the one that's just right. And so this is the T1. Okay. And so we have most efficient relaxation when that tumbling rate is close to the Larmor frequency, when we are too in macromolecules where it's the tumbling rate is too slow, then the T1 is very long. And also in free water, when the tumbling rate is too fast, also the T1. Okay. So we have to be sort of some way between solids and liquids to get the right tumbling rate. The other thing is that the tumbling rate of most objects is down here, so that as we go from this picture to this picture, this is going from a certain field strength to a higher field strength here. Remember, the frequency of precession is the Larmor frequency, which is proportional field strength. So as I increase the field strength, I move out along this axis, okay? And therefore, there tends to be much fewer spins that are tumbling at the right rate. And so therefore, as I go to higher field strength, this T1 recovery is longer, the T1 time constant increases. It turns out that in the body, fats and oils tend to have, for the clinical field strengths that we typically use, like 1.5 or 3T, they just tend to be vibrating or tumbling at the right rate. So they typically have very short T1s. That's T1. Now here's T2. T2, once again, as you can sort of see, has quite large variation. So here in brain and white matter and muscle, you can sort of variation in the hundreds to 43 milliseconds. And then you notice for liquids, so CSF stands for cerebral spinal fluid, which is the liquid that bathes your brain. It has a very long T2, almost 4 seconds, which is basically the T2 of water, because it's mostly water. Okay. So it turns out that liquids have relatively long T2 values, and we'll talk about why that is. And solids actually have very short T2 relaxation. Okay. So there's also a big difference now between solids and liquids. And remember, T2 happens when, after excitation, we assume the spins are in phase, and then they get out of phase. Okay. And as they get out of phase, they it's destructive interference, and so they sum up to a smaller number. Okay. So the question is, how do spins get out of phase, and why does that depend on whether it's a solid or a liquid? Okay. So one way to think about it is, if I'm a spin here and I'm just spinning happily along, right? Now I'm surrounded by all these other spins. Okay, so maybe this spin is tumbling at one rate, and this spin is tumbling at another rate. So this spin might be giving me, and I'm experiencing the magnetic field from all these spins, right? So if these spins are just tumbling really fast, right, then they're all sort of, if like this is saying go slower and this is saying going faster, and you have so many of them, and they're all, so the ones that say go faster cancel out the ones that say go slower, because they're all tumbling so fast. So that's what's called motional averaging. That basically, if the signals you're getting from the surrounding spins are just so quickly changing so fast and they're all canceling each other out, then here it's almost like all the effects cancel out. Okay, so there's going to be very little change in my precession rate, because whatever this spin tells me to do is canceled out by another spin. Okay? So that's in this regime here, where we have very quick tumbling rates, so things can average out over the time constants we care about. On the other hand, you notice here in this regime, when the tumbling rate is very slow, then we get very short T2s. And the reason for that is, imagine here now things are just going like this. So they're both sort of saying go faster or go slower, sort of in sync. Okay. So in that sense, the net effect on me will tend to get, if I'm here, maybe I'll go faster. And if I'm another spin here and I see some different environment, I'll go slower. And so now all these spins get out of phase. Okay. So that's sort of the intuitive way to think about it. Obviously, there's much more we could say about that, but for this purpose of this course, that's sort of a good basic level of sort of intuitive understanding. So these are some basic, let's look at these T1 values. So you can sort of see here for water or CSF, we have very long, both T1 and T2, right? Because the T2 is very long because mobile spins in liquid can tumble very quickly. Okay. Notice what happens when we go from water to ice. Now the T2 goes from 2 seconds to 0.0, like 1 millisecond. Because now the spins can't vibrate, and so they're not going to average out their effect. And so as the spins in the ice are sort of in sync with each other, then they have more net effect on any other spin. But the T1 stays very long, okay? Because the vibrations are not tuned, right? The T1 has a tuning curve, right? The vibrations have to be at the right frequency, and if they're either too fast or too slow, so in this case, the ice is just, this is for 1.5 feet, just not at the right tuning curve. Okay. Let's look at something else that has a very short T2. So tendon, right, tends to be very short T2. Another thing that would have very short T2 would be cartilage as well. So things where spins are not very mobile, and a relatively short T1 as well. Okay, so to get some sort of give you some practice with thinking about this, let's do this one additional exercise, I believe. So here's the scenario. You have a vial of liquid. So Dr. Block has a vial of liquid with a T1 of 1,000 and a T2 of 1,000. So this is made up. Now you add some gelatin to the vial, okay, and then you let it gel. Now you go back and measure it again. What would be reasonable values for the T1 and T2 of the mixture? Okay, so go ahead and think about that for a minute, and we'll regroup in it. About another minute. Okay, so looks like most people online have responded, so that's great. So let's see what the everyone in person has sort of concluded. So at the count of 3, just go ahead and say loudly whatever you feel is a reasonable answer. So 1, 2, 3. Okay, so I think I heard B, D, and E, but maybe focus on D and E. So let's take a look at these. So online, it was mostly D and E, and then some for A and B. Okay. So what would be reasonable? So obviously, if I put in gel, then the tumbling rate is going to go down, right? So we know at least on the T2 curve, right, we're going to move this way, right? So T2 has to go down, okay? So we're going to get rid of these guys. So the other thing is, what we didn't really emphasize, but I'll emphasize now, is that T2 is always lesser than or equal to T1. Which we talked about a little bit, but now we'll just say it turns out the physical mechanisms that give rise to T1 also cause T2. And so it turns out that for the magnetization not to exceed equilibrium magnetization, T2 has to be less than or equal to T1. So therefore, we can also rule out this one and this one. Okay. So we're just left with D and E, which turned out to be the most popular choices. And the question is there actually a way we can differentiate these two? So we can also, so this is the T2 curve, right? And we know the T1 curve goes like that, right? So now it really depends on where we are, right? So for example, if we were here, then we would move this direction, right? And the T1 would get longer. But we could have been here and moved in this direction, in which the case the T1 would get shorter. So in this case, both D and E would be reasonable answers, assuming that you didn't know anything else. Any questions on that? Okay. The next thing we're going to talk about is the last kind of relaxation, which happens in the real world, which is we spend a lot of time and money, the manufacturers, on having a very uniform field. So if you go in and look at the B0 field, it's very uniform. But then it turns out that anytime you put a biological object into a main uniform field, it will distort the field around it. Okay. So that's shown here, where, for example, you may remember that there is both and ferromagnetic materials that tend to concentrate the field. Okay. And there's diamagnetic, which tends to repulse the field. Okay. And so you can sort of see here, for example, diamagnetic would be things like water. Paramagnetic is things that have like iron, and then ferromagnetic is opposite iron. Super paramagnetic is ferritin. So anything that sort of can be magnetized will tend to concentrate the field. And anything that is sort of has the opposite will tend to repulse the field away from it. So what that means is we've gone from this very uniform field to now changes in the field. Okay, so and this is something that we really can't get around because all biological, we're not really interested in imaging uniform objects, right? It's not that interesting. Biological substances have a lot of things in them. They're all going to tend to have different magnetic properties, and so we're going to be sort of stuck with this this problem. So here's an example that happens a lot. So what you're showing here is you're seeing different slices of someone's brain. And here what you're plotting is what's called field map. And so the dark and bright just means that these have different field strengths to them. So can anyone hypothesize why there'd be these big inhomogeneities in the field? So it's relatively uniform here, but it's very inhomogeneous field. As I'm going from here to here, the field is clearly changing a lot. So why would there be such strong field homogeneities here at sort of the front of the head? What's going on at the front of your head? Any ideas? So we're about to enter flu season, and So hopefully everyone's gotten a vaccine. But if you don't get a vaccine and you get a flu, you'll be sneezing a lot, right? And what other thing, like, where does the congestion, like if you have congestion, what is that called, right? It's like sinus congestion. So what are your sinuses? Anyone know? Like if you have a headache here, like if you have a cold and you have a headache, oh, you have a lot of pressure here, right? Does anyone know what your sinuses are? There shouldn't be fluid. If there's fluid, you have a problem, right? So actually, yeah, that's the problem. When you have an infection, your sinus is filled with a lot of gook and yucky stuff, right? And you have to get that out. So the sinuses should be filled with air. Okay. So you have all these air pockets around this area of your head, right? I'm not sure what the latest thinking is why you have sinuses. It might just be to make your head lighter. I'm not really sure, but you do have these pockets of air, and so that's what's happening. That basically you have tissue and air, and they have very different magnetic properties, and so that leads that homogeneity. Air, vacuum, and sinus. Yeah, great. Okay, bones. Yeah, good. Okay, so there was I didn't see it, but yeah, someone mentioned sinus. Okay. So this actually turns out to be a very big problem because it's basically a very strong source of inhomogeneity. And so why does that matter? Well, if you think about, if I have spins that are all lined up and then I put them in the presence of some inhomogeneous field, then because every spin feels a different field, they're going to start to process at different frequencies, and so they're going to get out of phase. Right? And if I measure it some later time, this TE stands for echo time, the very important quantity that we'll keep using now. Then there's going to be some dephasing, so some signal decay. Now, if I increase it in homogeneity, such that there's a lot more homogeneity, let's say I get close to a sinus cavity, then now the spins experience much more variation in fields. And so they're going to get even more out of phase, and there's going to be an even bigger decrease in my MR signal. So that's just shown here, where basically previously we've only talked about T2 decay. Now we're going to add this term T2 prime to account for this added decay due to static indicators. So this T2 was due to random tumbling. That's from random motion. This T2 prime is actually static indicators. And so the way we represent that is we say we're going to introduce something new called T2 star, which is our effective relaxation time constant. This could also be written as R2 star equals R2 R2 prime in terms of rates. Okay, so it just means we have a certain rate that's due to random motion, and we add to that an additional rate that's due to these static inhomogeneities, and then the overall is R2 star. Okay, so effective transverse relaxation rate. Or if it's the T's, it's time constant. Okay. So you can talk about rates or time constants. Then the interesting thing though is that one of these is reversible. We can actually get rid of one of these. So the T2 is obviously due to random motion. It's random, so there's really not much nothing we can do about that. But this is due to something that we should be able to measure. And so in principle, it should be reversible. And it turns out we'll end this lecture with a discussion of the spin echo sequence. Okay. So previously we've talked about gradient echo sequences, and these are what exhibit T2 star decay. And as we said before, that gradient echo is simply the refocusing done by these gradients that gets you back to the center phase space. So what that means is if you, example of your signal, let's say you measure a rect function, so the Fourier transform is a sinc function, you expect to measure a sinc function as your MR signal. But because of this T2 star decay, this exponential decay, you actually measure a much smaller signal. Okay? And if you go out farther and farther, it's going to decay even more. And if you go out too far, you're going to have no signal to deal with. Your image will just look black. And that's exactly what you see with gradient echo imaging. Okay. So this person here I mean, this looks pretty bad, right? I mean, like, is this person missing a mouth? What's going on? What do you think is going on with this picture? Let's say I told you this person is perfectly healthy. So what do you think this person has? They must have something in their mouth that's causing this decay. So any guesses? Like, what do a lot of teenagers, you go to the dentist and what happens? You get braces, right? So this person probably has a lot of dental work. Probably a lot of the old-fashioned braces, not the new Invisalign or whatever the latest thing is, right? There's probably a lot of metal in their mouth, right? Which is going to perturb the magnetic fields quite a bit. So this person should never have gone an MR scanner in the first place, right? But they did. So, and this was the image that here. In this case, there's probably some metal implants. And whether this person should have gone in the scanner or not, depends a little bit on the safety criteria of the implants. But in general, we try to limit people to like titanium implants or things like that. And if this was steel or ferromagnetic, it would obviously also be very dangerous for that person. Okay. But in any case, these people, when they're imaged, clearly had metal that was causing these imaging. So the way we get rid of it is actually a very clever trick invented by Erwin Hahn in 1950. So Erwin Hahn, we talked about before, was this famous MR physicist, was a professor at Berkeley for like 60 years. I think he just died a few years ago. And so here's the idea that spins get out of phase, right? So imagine if these are my spins, they're originally in phase, then they get out of phase, okay? So like this spin here is going faster, and this spin here is going slower, and this spin here is at the right rate. Okay. So over time, they get out of phase. Now, what if you could have an RF pulse that is, after waiting for them to get out of phase, at some point in time, you could flip the orientation of the spins, such that now the fast spin is at the back and the slow spin is at the front. Okay. Now this spin is going to go fast, so it's going to catch up. This spin can go slow, so it's going to lag behind. And at some point, they're all going to be back at the same rate. Okay, so that's what's called rephasing with a spin echo. Okay. It's as if you had a race, right? Let's say we ran a race, and after 10 minutes, some of us were at the front, and some of us were at the back. Right. And then at that point, like 10 minutes in the race, we say, okay, everyone in the front, you go to the back, and everyone in the back, you go to the front. And we run another 10 minutes. If we're all running at the same rate, at the end of that second 10 minutes, we'll all be at the same. All be gathered together again. So that's another way of looking at it. So that is exactly what the spin echo does. This is sort of a movie where they get out of phase, and we flip them, and they get back in phase again. So once again, the slow spins get flipped to the front, the fast spins get flipped to the back, and then they reconverge. So how do we do that? We do what's called a spin echo pulse sequence. So before we have this gradient echo, and then we have this over here. Now we impose what's called a 180-degree pulse. That 180 degrees basically takes all the spins and rotates them by 180 degrees. So that's the sort of pulse we want to go from fast to the back and slow to the front, right? And then we acquire data after that. And so, so instead of having this T2 star decay, we now have refocused the T2 prime component, such that we have a much bigger signal here. Yeah. And this is the last slide I'll show, which is basically showing what you can do with that. So this is a great echo image where they've somehow created some homogeneity, so you get these banding patterns here. Where here the signal is adding destructively, right? There's dephasing here. That same object, they just put in that 180-degree pulse, and all of a sudden, it's all been refocused. So spin echo is incredibly important for medical imaging because it allows us to get away from these signal dropouts. Okay, so it is one of those very, very standard pulse sequences that you will see on any clinical system. You'll hear about things like spin echo, fast spin echo, all different types of spin echo. Okay, so with that, that's all for today. So we'll pick up on relaxation again on Wednesday and talk about contrast and hopefully maybe even start a discussion with MRI. So I'm here to answer questions. Otherwise, we'll see you on Wednesday.
Professor, I have a quick question.
Yes, go ahead.
Yeah, for the T1 and T2, in terms of the project, right? So is it okay if we include maybe, I mean, I read something more about a T1 row, a T1 RHO, which is like an investigational technique. It's not authorized yet for the diagnosis purpose, but do you think if we can include that also in our project, will that add any value?
Oh yeah, T1 row would certainly be interesting and would certainly require you to do sort of a deep dive into how that works. And it also involves, what sort of RF pulses you would need to do that.
Sure, yeah, okay. Yeah, so we'll definitely explore that. Thank you.
Okay, great.